that the chair will be María Ángeles Laguna. She is a researcher at the Institute of Nanoscience and Materials of Aragon here, which is an institute of the Universidad de Zaragoza and the Spanish Council for Research. She performed her PhD here in Zaragoza, and after that she has been as a postdoc in Argonne National Laboratory, well, exactly at the Advanced Photon Source at the Synchrotron near Chicago, also at the Instituto de Ciencias y Materiales de Madrid, of the Research Council in Madrid, in Spain, and then she came back to Zaragoza, and recently she got a permanent position as researcher here. So, María Ángeles, it's my pleasure to give you the floor. Please, thank you very much.
Thank you, Fernando. Once again, welcome everyone to this new session of the School of Spintronics of the Spanish Network on Spintronics. This afternoon, we have 3 different lectures, and we are going to start right away with the first one, which is given by Professor Tomas Jungwirth, who is head of the Department of Spintronics and Nanoelectronics at the Institute of Physics of the Academy of Science of the Czech Republic, as well as professor of the School of Physics and Astronomy of the University of Nottingham in the UK. Tomas Jungwirth received his PhD degree in condensed matter physics from the Charles University in Prague in 1997. Subsequently, he has worked as a postdoctoral fellow at the Indiana University and as a research fellow at the University of Texas, both the US, before joining both the University of Nottingham and the Institute of Physics in Prague. In 2018, he was awarded an ERC advanced grant in the field of spintronics, and he has been a member of the ERC advanced grant evaluation panel, among many other memberships. His field of expertise is in theoretical condensed matter physics and includes electronic properties of nanostructures, quantum Hall effects, magnetotransport and magneto-optical properties of ferromagnetic semiconductors, and quantum relativistic spin-orbit coupling phenomena, as well as spintronics on antiferromagnets, which is the topic he's gonna talk about today. So Tomas, thanks for accepting our invitation, and you can share your screen and start your lecture when you are ready. Thank you.
Thank you, María Ángeles, for the introduction, and Fernando et al. For inviting me to this school of Spintronics and for organizing the school. So recently there has been a rapidly increasing interest in antiferromagnetic materials, and here the primary motivation has been a possibility of using antiferromagnets in spintronics. And there is certainly no way that I can cover this fairly broad field as it has become over the past several years. So at least let me acknowledge a few of the groups that have been contributing to the field and have also prepared review articles on antiferromagnetic spintronics. And already from the titles, you see that it's a field that covers many different areas, from electronics to dynamics, spin textures, optics, and also connection to other fields, including topological condensed matter physics. Regarding the outline, so I'm gonna say only a very few words about ferromagnets as a benchmark or as a comparison. I understand that there has been a lot of introductory talks already on spintronics, and I believe that 99.9% has been about ferromagnetic spintronics. I'm going to then move to antiferromagnets, again in the context of spintronics, but I'm going to spend only several slides on antiferromagnets, and will devote most of the talk to a newly delimited class of magnetic materials, which we call altermagnets. And we will see how all these three different magnetic classes are related to each other, and also what's their relevance, in particular, what's their relevance for spintronics. So this is the one and only slide devoted to the main part of spintronics, which obviously is based on ferromagnetic materials. So in ferromagnets, the big advantage that we have is that we have these magnetically ordered atoms in the lattice here. They're typically atoms of the 3D elements like iron, cobalt, or nickel. And these magnetically ordered atoms, they act through their exchange field on the carriers, and they would polarize their spins. So if you look at the electronic structure of the carriers, you see that the spin up and spin down bands are split by this exchange field generated by the magnetically ordered atoms here. And if ideally you have a Fermi level in a part of the band structure where you have only one spin occupied, you have a perfect spin polarization of the carriers. That, of course, does not happen in most of the ferromagnetic metallic systems, but still they have a high, or they can have a high level of spin polarization of their carriers. And once you have these basically non-relativistic spin polarized bands and carriers in these bands, you can do the key functionalities that govern the commercial spintronics. There are the functionalities for reading the magnetic information, whether it's a giant magnetoresistance or tunneling magnetoresistance, in which case you have your device split into two magnetic parts. One magnetic part serves as a reference from which electrons are injected with a defined orientation of the spin polarization. And the second part is the recording or the sensing element, which then detects whether the two layers in the device are polarized in a parallel or in an anti-parallel fashion. So once you send a probing or read out electrical current through such a device, what it does is that it injects from the reference ferromagnet the spin polarized electrons, and they are injected into the sensing or recording film on the device here. And now when the two ferromagnetic electrodes have a parallel polarization, then it's easy for the electron carrying its spin to travel from the reference to the recording or sensing film. However, if the polarization of the recording or sensing film is opposite, then it's difficult for the electron to move from the reference to the other layer, because it would have to flip its spin in order to be able to be absorbed in this other layer. So in the anti-parallel configuration, you then typically have a high resistance state, and in the parallel configuration, you have the low resistance state. You can also use the same device and the same property that you can inject spin polarized carriers, but now apply a larger electrical current. And when you do this, when injecting the spin polarized carriers from the reference to the recording layer, if you inject enough spin angular momentum, you can induce a reversal of the magnetization of this recording ferromagnet. And so this is the so-called spin transfer torque mechanism for electric writing, using, again, these spin polarized currents. Now let me move to these 3 or 4 slides about antiferromagnets and their utility in the research of spintronic devices and phenomena. I'm emphasizing that this is research because we do not have yet commercial devices whose active electrodes would be based on antiferromagnetism. But as you will see, there are research examples that in principle antiferromagnets can be used also in the spintronic devices. Now, what is the main motivation to look into antiferromagnets as complementary materials to ferromagnets? Well, the whole field started about a decade ago, and here people envisaged basically three main advantages, potential advantages compared to ferromagnets. First of all, ferromagnets typically are metallic, while in antiferromagnets you can have a richer landscape of material types from the conductivity or conduction perspective. Antiferromagnetic materials can range from insulators, semiconductors, to metals, but even superconductors. So in principle, one can envisage a more exotic or a variety of device types if you replace the active electrodes, ferromagnetism, if you replace with antiferromagnetism. The other attraction to antiferromagnets is that they are basically magnetic dipole free, which means that they are much less sensitive to disturbing magnetic field, which is one of the limiting factors in ferromagnetic spintronics. They also do not generate their own magnetic stray field, so there is no unintentional crosstalks between antiferromagnetic bit cells. And finally, because of the antiferromagnetic order, they have a much faster dynamics, while ferromagnets and ferromagnetic resonance is typically in gigahertz scale. Antiferromagnets tend to have a terahertz scale dynamics, which also gives a possibility that operating these devices can be at orders of magnitude higher speeds in principle than in ferromagnets. However, there is obviously a major obstacle, and there is a reason why antiferromagnets for so many decades have actually been ignored in microelectronics and in principally many practical applications. And the reason is that we have now anti-parallel moments sitting on neighboring magnetic atoms here. And as a result, electrons and electronic states in the band structure, if you look at an individual momentum state or K-vector state, in such a lattice, it would be an equal mixture of states originating from one magnetic sublattice and also from the opposite sublattice. So you have a mixture of spin up and spin down states at each K-vector here. So your electronic structure, and that means also your current carrying electrons, are spin unpolarized. So none of these effects that I showed on the previous slides, giant tunneling magnetoresistance or spin transfer torque, are directly then applicable in antiferromagnets. So when people started thinking about using antiferromagnets in electronics, and again, you asked the question, how are you going to detect the direction of the magnetic order, in this case, the antiferromagnetic order, and how are you going to electrically write or manipulate the order? So if we start with detection, well, fortunately, we already know from ferromagnets that there is a detection mechanism of the magnetic order, which does not necessarily rely on spin polarization of carriers. And this phenomenon is known due to Kelvin by for more than 150 years, and it's called the anisotropic magnetoresistance. Of course, Kelvin did not understand the microscopic origin of this phenomenon. He only observed that by running electrical current through a ferromagnetic material, the resistance depended on the angle of the magnetization. And today we know that on the, let's say, lowest approximation level, we can understand this effect as having unpolarized electrons, which are scattered of these magnetically oriented atoms in the lattice. And then because of the relativistic spin-orbit coupling on these magnetic atoms, the scattering of this basically spin unpolarized electron would depend on the angle of the magnetic moment with respect to lattice vectors here. So because this phenomenon in principle does not require spin polarized carriers, the idea was that it should be directly transferable from ferromagnets to antiferromagnets, because we said, fine, in antiferromagnets, we do not have spin polarized carriers, but we still have magnetically ordered atoms. And so now when the magnetic moments change their angle, let's say by 90 degrees, the spin orbit coupling scattering of these magnetic moments should then again result in resistance of the material depending on the angle of these antiferromagnetic moments. And indeed, that has been observed. It's been shown that the effect is equally strong in antiferromagnets as in ferromagnets, and in many antiferromagnetic materials, this phenomenon since that has been already demonstrated. So I'm not going to show you a specific demonstration, but in this review article from 2016, you can already have a number of examples of antiferromagnetic materials where you can detect the angle of the antiferromagnetic nail vector by anisotropic magnetoresistance. Now, how are we going to control the antiferromagnetic moments? How are we going to write the direction or the angle of the nail vector here? So again, we are not going to rely thinking that antiferromagnets do not have spin polarized carriers on injecting spin currents like we do in ferromagnets. But what we can do is we can inject an unpolarized current in an antiferromagnet. But then if an antiferromagnet has a special local symmetries of these sites, in particular if the inversion symmetry is broken on a magnetic site, and if we include again relativistic spin orbit coupling, what can happen is that the electrons, the current that is injected into the antiferromagnet, it will develop a polarization. So the carriers will be polarized with one direction of the spins at one of the two magnetic sublattices. And with the opposite spin, the polarization of the carriers will have the opposite direction at the opposite magnetic lattice. And again, this direction of the spin polarization is independent of the magnetic moments. It is just defined by the local symmetry or local inversion asymmetry of the site, of the crystal site, and by relativistic spin orbit coupling. So you can generate this staggered or alternating spin polarization at these two sites, and the magnetic moment will then align with this non-equilibrium spin polarization. But as you see, it's local, but when you sum up these polarizations of the carriers over the unit cell, you will get zero. So there is no net spin polarization. You only generate a spin polarization locally inside the unit cell with one sign at one side and opposite sign at the opposite side. And it only happens in a non-equilibrium state. So we have this, we have the means how to electrically read through an isotropic magnetoresistance and write through this relativistic local spin polarization. So here is an example of physical realization of this concept. The material that has been a workhorse in these antiferromagnetic devices is antiferromagnetic copper manganese arsenide, where the manganese is magnetically ordered in this antiferromagnetic fashion here. You can then fabricate micro devices in which you can either change the polarity of the writing current, or you can change the angle of the writing current. In both cases, it is possible to change the orientation of the nail vector by 90 degrees. And this is the change that you need to be able to detect it by an isotropic magnetoresistance. But before doing the electrical measurements, it's always very important to do a detailed microscopy to make sure that what happens in your device is indeed the electrical signal that you detect is indeed of magnetic origin. So here is a movie which is taken at synchrotron using X-ray microscopy. And it's a special X-ray microscopy in which the contrast, the light and dark contrasts correspond to orthogonal directions of the nail vector. So for example, the horizontal direction of the nail vector would be a dark domain, and the vertical one would be a light domain. And you see that by pulsing these devices, either by changing the polarity or the angle of the pulsing current, you can reversibly switch between the dark and light domains here, which represent one or the orthogonal direction of the nail vector. So this is microscopy, and below it's a corresponding electrical signal, and in such a device due to the anisotropic magnetoresistance. And you can see that for if you would fabricate, or if your domain is switched in this central region of the device between the light and dark, you see the low and high resistance states corresponding to logic 0s and 1s. And this is not a cartoon, this laptop. Indeed, you can place these antiferromagnetic bit cells on experimental printed circuit boards. You can connect these printed circuit boards to your personal computer, and you can operate the device at ambient conditions on your desktop. So this is obviously not a commercial memory device, but it's just a device which demonstrates that in principle, antiferromagnetic memories can be operated using conventional electronics. Now, one last slide on antiferromagnetic spintronics. And here I show you an example that you can do many more tricks with antiferromagnets than just making digital memory bit cells. So here is an example of again, antiferromagnetic copper manganese arsenide device, which in this case is patterned into a simple resistive bar device, which you can think of just a 2-point resistor in which you can send a right pulse between these two contacts, and you can then measure the voltage, how the voltage changes in response to the pulses. So in this case, the device can even be operated in a unipolar way, where you apply the right impulses only in one direction. But what you do is you change the amplitude of the pulse. And here, what is shown is a functionality. When you send a strong pulse here, then you write a high resistive state into the device. And then without pulsing it, you see how the state, the resistance slowly relaxes towards a lower value. At this point, you can send a weaker pulse. And what happens is that you actually suddenly change the resistive state into a low or lower resistance. And again, it's followed by this smoothly relaxing process. Or you can reverse the order. You can first submit the weaker pulse and write this lower resistance state, then let it relax a little bit, send a stronger pulse, and you will write this high resistance state. And again, it will relax. So what you see here is a time-dependent memory logic functionality where the state on the device depends, first of all, on the amplitude of the pulses, on the order of the pulses, and also on the delay between pulses. And so again, to demonstrate, so this is a measurement in lab using very accurate measurement instruments. And what you see here is that this rather complex memory logic functionality is fantastically reproducible in these devices. And here again, I'll show you a demonstration that you can bring the device. It's an analog device. Now you can put on an all analog board, and you can bring it to a test site where you have a sensor sensing a vehicle, for example, and another sensor sending a weaker pulse. And you see that you have the same falling edge as in this case, where the weaker pulse was the second one. And now when the vehicle comes in the opposite direction, our memory logic device will first get the weak pulse and then the stronger pulse, and you see here the rising edge. So this is a demonstration that with such an antiferromagnetic device, you can perform, and it's just a 2-point simple resistor-like device, but you can perform a fairly complicated memory logic functionality in which you can detect coincidence and causality here, and then automatic reset, and again, operate the device again. Now, what is the basis of this functionality is not a simple domain reorientation of the nail vector, but instead it's actually that you are changing the domain morphology. let's say from a large domain state, you're moving into a nanofragmented domain state. And that allows you to generate many different metastable states in your antiferromagnetic device. And what is quite remarkable that this can be done in a completely reversible and reproducible fashion. What can be also done in these devices can be shown that you can reduce the pulse length by which you write it from the electrical microseconds down to nanoseconds. You can go to optical pulses and write these states by ultra short laser pulses, scaling it down all the way to a single femtosecond laser pulse. And what is remarkable when you do a very detailed microscopy by transmission electron microscope, what you see here is that by these pulses, you can generate textures in the magnetic states, which are the smallest you can possibly imagine in a magnetic material. Here is a cartoon where you see a domain wall here, which is actually atomically sharp. So the reversal of the neovector happens between two neighboring atoms here. And this is the microscopy image from the Lorentz transmission electron microscope that shows you that indeed you can have domain walls, so you can have textures which are atomically sharp. And that just tells you something about the scalability of these devices. You can really go to very small dimension and still being able to generate many domains separated by these ultra narrow atomic domain walls. Okay, so this has been these few slides about first ferromagnetics, standard ferromagnetic spintronics. Then I moved to a few examples of the research and development in devices using antiferromagnets. And now let me move on to this third class of magnetic materials, which I'm going to call altermagnets, and see what we can potentially do with these type of materials and what are they? How can we theoretically delimit this class? So I'm here moving actually back to the non-relativistic fundamentals of collinear magnetism. So no relativistic spin-orbit coupling, simple collinear magnetism. And I'm asking myself the following question on this cartoon. So we've seen that if we have ferromagnets where all the magnetic moments are pointing in one direction, we can generate these spin polarized carriers because we have the exchange split bands. We also seen that if we take this antiferromagnet, the action or the effect of the two opposite sublattices is that the band structure is spin unpolarized, because every momentum state is a mixture of a spin up and spin down state. So effectively there is no spin splitting of the bands. So the question I'm asking here, is it possible still in a magnetically compensated system? So I have the same number of spin down and spin up moments or magnetic atoms in my lattice, but is it possible to still extract spin polarized carriers from this? In which case I would be able to combine advantages of the antiferromagnetic spintronics with the phenomena and functionalities which are driving the ferromagnetic spintronics. So basically what I'm trying to accomplish is that, is it possible that I will be looking or somehow extracting spin polarized carriers with one spin when I be looking through my lattice in one direction, and if I would look through my lattice in a different direction, orthogonal in this cartoon, I will be able to extract the opposite spins. So on this cartoon level, I will be looking at some momentum here and extracting spin up. And when I rotate the momentum by 90 degrees, note that this axis is not plus minus, it's not inverse, but it's rotation by 90 degrees here. So I will rotate my momentum by 90 degrees and I will be able to get the opposite spin polarization. Is it possible, and if so, how? So, and in the rest of this lecture, I will try to explain on a very fundamental theoretical level that this is not only possible, but that there is a whole class of materials which have exactly this property, and that this class is basically as common or as abundant as the class of the spin unpolarized antiferromagnets or the spin polarized ferromagnets. And so to be able to formally delimit this third class, I have to be somehow able to understand from symmetry perspective non-relativistic collinear magnets. So the first question, so I'm going to now, before I delimit this class, I will now need two preparatory slides in which I will do a very quick wrap up of basic understanding of symmetry groups. But I will not go to any details. I'll try to make it on a very basic fundamental level. And on this slide, what I am trying to explain or argue is that I need to use a special type of symmetry groups, the so-called spin groups, in which real and spin space symmetry operations, rotations in particular, are not coupled. And that's very important because if you would now go to most of the magnetic literature today, people use magnetic groups, which are relativistic. It means that when you do a symmetry operation, for example, rotation, you will simultaneously rotate the real space, the crystal, and spin. And it's important to do this when you're interested in relativistic phenomena. However, we are now going back to the fundamentals of non-relativistic magnetism. So we do not want to have the symmetry operations coupled in the real and spin space. Another advantage of these relativistic magnetic groups is that you cannot even distinguish in principle, between different types of magnetic classes. For example, between a ferromagnet and an antiferromagnet. Here is an example of a ferromagnet, which has a rotational axis symmetry. So I have this axis, and as you see, I can rotate along this x-axis here, and nothing will change. So after doing this rotation operation, I will transform this crystal into this one. So they are identical, so it's a symmetry. And as you see, I can have just one moment orientation for all my magnetic atoms. Now, when I go here to the bottom here, I have an antiparallel configuration of my magnetic atoms. You would think that this corresponds to an antiferromagnet. But now when I do this rotation around the same axis here, when I do the rotation and I do it in this relativistic magnetic groups, I rotate the crystal, but I also rotate the spins. And by this, I will actually recover the same state. So I have a ferromagnetic system and I have this antiferromagnetic system, and they all have exactly the same symmetry. So these magnetic groups are not able for me to provide me a distinction between non-relativistic and relativistic, and even a distinction between a ferromagnet and between an antiferromagnet. So let's take a look at our spin groups in which these real space and spin space rotations are decoupled, whether this is going to help me. So again, I'll start with the ferromagnet and I'll do the rotation here, and I get the same state. That's fine. Now, when I go to my antiparallel configuration of these two magnetic atoms, and I do only the crystal rotation, but I will fix the orientation of the spins because the two spaces are uncoupled. So when I only rotate the spin, my purple atom will move on the green side, the green atom will move to the purple side, but the arrows will not flip because I'm only rotating real space and not the spin space. So you see that now in my system with antiparallel moments, this rotational, crystal rotational operation is not a symmetry. I have to add another symmetry operation, which is now an independent rotation of spins in the spin space here to recover the original state. So my ferromagnet has just this crystal rotation symmetry, but my antiferromagnet has a crystal rotation combined with the spin rotation. That's the symmetry. It also tells me a very important thing, this symmetry here, that imposes that it's actually a perfectly compensated system. This crystal rotation tells me that I can map one sublattice onto the other by a crystal symmetry operation. And when I can do this, when I can map these two sublattices on each other by some symmetry operation, that means that the amplitude of the magnetic moments which are generated by exchange interaction, they have to be identical. because the two sublattices are connected by this crystal symmetry. And on top of this, because there is also the spin rotation I need to apply, it means that the moments are anti-parallel. So this combination of symmetries imposes that the two moments have equal magnitude and opposite sign, which means that the system is perfectly compensated. So this is the so-called transposing symmetry, because it transposes opposite sublattices. Here in this case, the symmetry operation was not transposing, was not mapping this side on another side with an opposite moment. So it was a non-transposing symmetry, and it meant that there is nothing that requires compensated magnetic state. So magnetization is non-zero, and I have a ferromagnet. So this transposing symmetry is very important to have a magnetically compensated system. But now the question is, isn't this really the thing that also imposes that my bands are going to be always spin unpolarized? Because what I do by this transposing symmetry operation is that I'm saying that in my crystal, I can map one sublattice on the other by a simple rotation or a simple symmetry operation. Once I do this, it looks like I'm perfectly compensating my system. I have two identical sides, one with one spin, one with the opposite spin. They will just cancel. And would that imply that always I will have spin unpolarized carriers? Well, in some cases it will, and in some cases it won't. And when it won't, this will be the third class towards which we are now heading. But let me introduce one final slide, a preparatory slide, before I show you the three delimited classes. And that is a slide when I will simplify my symmetry analysis. And I will simplify it by, first of all, realizing that I am talking about the energy bands. I'm talking about their K dependence and spin dependence. And here, as you see, they are invariant under translation, under crystal translations. If I apply the translation operation on a band for a given momentum and spin, I get the same. So I do not have to consider all the 230 crystal space groups, which contain also translation, but I can limit my consideration just to 32 crystal point groups. Those are the crystal symmetry groups which do not contain translation operation. I can do this because translation is irrelevant for my physics, and that's the physics of the electronic structure. Moreover, and that's remarkable for non-relativistic collinear magnets, I can also consider the presence of the following symmetry. It's a symmetry which combines time reversal and spin rotation. If I have any magnetic collinear magnetic state here, and I apply the time reversal, I flip all the moments. So I get this state. But when I apply then the spin rotation, I also flip the moments here. So I recover the original state. Now let's take a look what this symmetry. So my system always have this combination of time reversal and spin rotation symmetry. So that means that also my bands have to be invariant under this combined symmetry operation. So a band at K and spin has to be the same as a band on which I apply time reversal and spin rotation. So let me then apply this. And what I get is when I apply time and spin rotation on momentum, I get a minus sign because spin rotation doesn't act on momentum and time reversal flips sign. When I apply these two on my spin, I actually do not change the sign because rotation flips the sign and time reversal also flips the sign. So what I see is that acting by this only changes the sign of the momentum, but that's the same as doing inversion. So what I get here is that because my bands are invariant under the combined time reversal and spin rotation, they are also invariant under space inversion. So my bands are inversion invariants, and that applies to non-relativistic collinear magnets. So I can further simplify and only consider those of the 32 crystal point groups which have inversion symmetry. Or alternatively, I can consider groups without considering the inversion operation altogether. In either case, I'll just get 11 inversion symmetric crystal groups out of these 32. So that's my symmetry group landscape, which I need to describe my non-relativistic collinear magnets and their electronic structure. And so in these groups, I will have these 11 inversion symmetric crystal point groups, and I will add to this spin rotation operation. And this is the result. So I have now prepared all my theory that I can now construct a complete list of non-relativistic collinear magnets. And I can have these three cases. In one case, it's a ferromagnet, and ferromagnets are going to be described by symmetries which do not have this spin rotation element altogether. So I only have them described by my 11 inversion symmetric crystal point groups. And because I do not have this spin rotation element at all, nothing connects an energy band or energy state at a given momentum and spin with the opposite spin, because there is no operation which will flip the spin. So the band structure is in principle spin polarized, as it is in ferromagnets. Now, the second group is where actually the spin rotation is symmetry on its own, but that also means that it's a symmetry with in combination with all symmetry operations with the crystal point groups. Here, an example is an antiferromagnet which has a symmetry which combines space inversion and spin rotation. Because I am only considering the groups which have also space inversion on its own, I can then combine these two symmetries, space inversion and rotation of my antiferromagnet. And what you see here that it equals to having spin rotation as a symmetry element alone. And I can then do this. I can take my band, I can apply the spin rotation. I know that it's a symmetry, so these two states have to be equivalent. And that also means that my energy band at a k vector and spin and the same k vector and opposite spin have to be the same. So this means that I have spin degeneracy at every k point. And again, I have 11 of these spin point groups, which now describe my antiferromagnets. And finally, I get to the third class, which is the third possibility I can get in combining my crystal point group operations and the spin rotation. And that is when the spin rotation is not present on its own as a symmetry element, but only in combination with some crystal symmetry operations. And that some crystal symmetry operations cannot be inversion, because if it were inversion, it would be equivalent to having spin rotation as a symmetry. So it can be only something else, and that something else is rotation. So if I have a material which has a spin rotation combined with a crystal rotation, then I have a third class. And what then can happen is that this crystal spin rotation is mapping a k vector onto a different k vector. And in this case, I can have spin polarized bands, because an energy at an opposite spin is also at different k vector because of this symmetry. So I have a fully compensated system. I have zero magnetization, but nevertheless, I do have spin polarized bands. And I have 10 different spin point groups which can describe these altermagnets. So these systems are in principle nearly equally abundant as these 11 spin point groups describing antiferromagnets or 11 spin point groups describing ferromagnets. So, and with this theory, I can then list all the possibilities. I can have all these 10 spin point groups. But important thing is that from these spin point groups, I can also see how is the spin polarization in my band structure going to look like? What is going to be the topology? So here you see one type where you see one spin polarization. You rotate the k vector by 90 degrees. You have an opposite spin polarization by 90 degrees. Again, opposite spin polarization. So the spin flips twice. So you have a winding number 2. But you can also have 4 times flip here, so you have a winding number 4, or even 6 times flip, depending on the crystal symmetry. And with this, you can also go back to your database of magnetic materials, where so far people have ascribed only these relativistic magnetic groups. So you have to go through each individual magnetic material and reassign to it this spin point group. And once you do it, you can distinguish whether it's a ferromagnet, antiferromagnet, or this third spin polarized altermagnet. And we've done the job already for a few materials, and you can see that you can find metallic, insulating, many different types of these altermagnets with spin polarized carriers. Now, I'd like to emphasize that this spin polarization and this winding or topology might be somehow reminiscent to relativistic spin polarized band structure, where also your spin changes where you rotate. But here, the important thing is that here we have a collinear system. So you have only spin up, spin down, spin up, spin down. While here in relativistic system, because of the relativistic spin orbit coupling, the spin quantization axis actually changes, the angle changes when you go around the Fermi surface. Also in these non-relativistic altermagnets, as I said, the bands are inversion symmetric. So when you go from K to minus K, you have the same spin. In relativistic system, it's inversion asymmetric. When you go from K to minus K, you get an opposite spin. So we have these, to summarize, we have ferromagnets with spin polarized bands, we have antiferromagnets with unpolarized bands, but then you have the whole family of these altermagnets which have spin split bands. And what is the relevance of this for spintronics? So let me jump over to spintronic possibility here, where we have now this spin polarization, which you see can change from down to up when you go around the Fermi surface here. And it's in this anisotropic fashion. So now what we can generate in these altermagnets are non-relativistic spin currents in pretty much the same way as in ferromagnetic system. So imagine that you run electrical current here in the system. And as you see, because of this anisotropy, you will generate more spin up electrons for this current direction than the spin down electrons. So you have a net spin polarization of the non-relativistic current. When you apply the current in the orthogonal direction, you will now have a majority of spin down electrons. So it behaves like a ferromagnet in the way that you can generate spin polarized current, but it's also very different from a ferromagnet because the spin polarization of the current depends on the direction of the electrical bias that you apply. And when you apply the bias in this diagonal direction, you can generate a scenario in which the longitudinal current is spin unpolarized. So this is as if the system was antiferromagnetic. However, when you look at the transverse direction, in the transverse direction, you have a spin current. So this is something which is neither antiferromagnetic light nor ferromagnetic light. Such a scenario you cannot generate in a ferromagnet or in an antiferromagnet. And you can have a very large conversion ratios between the charge current and the transverse spin current, which is actually larger than a vast majority of the relativistic systems. For example, the relativistic spin Hall charge conversion systems, where typically the ratio is of the order of 1% because it's relativistic. Here you convert charge into spin current, transverse spin current with a conversion ratio of tens of percent. And finally, you can go to the typical, in principle, to the typical phenomena that you know from ferromagnets, like, for example, giant magnetoresistance, spin transfer torque, where again, if you have such a bilayer, and this is in the anti-parallel configuration of the nail vector here, of the altermagnetic nail vector, If you run the electrical current along one specific direction, it corresponds to the anti-parallel configuration of a ferromagnet. So it will be the high resistance state. Now, when you reverse the nail order, for example, here at the bottom electrode, now, and again, keep the same current direction, you will have the configuration corresponding to a parallel magnetization or parallel spin polarization of the majority currents. So this would correspond to the low resistance state. So to conclude here, we have shown, and you've seen in the lectures in the first week, that ferromagnetism utilizes spin polarized currents, and this is the vehicle that is driving the commercial spintronics. Now in antiferromagnets, and we now know how to theoretically delimit antiferromagnets within the non-relativistic magnetic materials. We have spin unpolarized bands. We do not have spin polarized carriers, but nevertheless, we were still able to, using relativistic physics, to do a variety of functionalities, including neuromorphic type of logic in memory or optical switching. But finally, what I focused on today is that you can delimit from non-relativistic collinear magnets third class, in which case you have still fully compensated zero net moment system, but your bands are spin polarized. So you can generate similar phenomena like in ferromagnets, but simultaneously take advantage of the zero net moment that been already demonstrated in antiferromagnetic spintronics. And as a final remark, I'd like to point out that these altermagnets may have a relevance to fields which go beyond spintronics. And here, as an example, this cartoon picture actually corresponds to a real material, which is apparent cuprate of a high temperature superconductivity. And this apparent cuprate actually belongs not to an antiferromagnetic class with a zero spin polarization of the bands, but its bands are spin polarized, and they are polarized in this fashion that when you go around the Fermi surface here, it goes from up, and down. So it has this winding number 2 or D wave, if you want, D wave symmetry. And the cuprate superconductors have also a D wave symmetry of their superconducting gap. So this opens a field of an interesting research of interplay between magnetism and superconductivity. So I thank you with this for your attention.
Okay, thank you very much, Thomas, for such a nice talk about ferromagnetism and altimagnets. Time is open for questions now. So while we are waiting for the first questions, I have a short question for you. Among the, let's say, most common, better known family of compounds, let's say rutile or pyrochlores or perovskites, is there any of these families that you can foresee that have most potential, more interest as altermagnets?
For example, you mentioned rutile. So ruthenium dioxide is a typical rutile system, which actually already Nail had these ruthiles in his original works. People consider those as being antiferromagnetic, and indeed they are compensated. They have zero magnetization. However, they in fact belong to the altermagnetic class from the perspective that they have spin polarized bands. And ruthenium dioxide is an example which have spin polarization of the order of 1 electron volt. So it's actually very strong, this non-relativistic spin splitting. It can have these examples of giant magnetoresistance or tunneling magnetoresistance. They've been actually calculated by ab initio for ruthenium dioxide. So it can have very, very large effects. its critical temperature is not as high, it's only around 350. So this is not something that would immediately lead probably to useful practical applications. But there are many examples which have very high critical temperatures, like for example, chromium antimony is another example which has 1.3 electron volt spin splitting. It's a perfectly compensated system, but had a very strong spin polarization and nail temperature around 700. And it's a very simple bimetallic compound of chromium and antimony. So you can have from oxides to bimetallic systems with variety of nail temperatures and variety of other properties.
Okay, thank you. One question about by Ricardo Rama Eiroa. Very nice talk. Thank you very much, Professor Jungwirth, regarding the existence of antiferromagnets in the form of insulators, metals, superconductors, and semiconductors. Could you explain a little bit more why this happens as opposed to ferromagnets?
There are, you can imagine many different perspectives, but one simple perspective is that in ferromagnets, if you want to maximize ferromagnetism and get high Curie temperature, you want to have a large splitting of the spin up and spin down states. And what happens is that if you would start from a semiconducting system with a band gap and now introduce to it also exchange splitting, then this exchange splitting would actually run through this band gap and you will get a metallic state. Another picture is that typically the way how you generate ferromagnetic order is by stoner ferromagnetism, which is from itinerant electrons and their exchange interaction, which leads to the ferromagnetically coupled ordered state. For antiferromagnets, on the other hand, the simplest picture is a super exchange. And the super exchange picture, you start from localized electrons and look how they hybridize between the magnetic atoms and the intermediate oxygen, for example. And so the picture to understand antiferromagnetism, the very basic picture is when you start from an insulating hybridization picture, while for ferromagnets, you start typically from metallic picture. This is how you get easy understanding why in one case you get a ferromagnetic order and in the other case antiferromagnetic order. Of course, in reality, the situation is much more complex. You have itinerant antiferromagnets. You can also have insulating ferromagnets, but in reality, in nature, insulating ferromagnetism turns out to be very rare. And the vast majority of ferromagnets are metallic, while antiferromagnets tend to be typically insulating, but there are many examples of metallic antiferromagnets, and there are, again, examples of superconducting antiferromagnets as well. And for superconductivity, you can also understand that antiferromagnetism is more favorable because if you have a ferromagnet, it's difficult to make a Cooper pair where you would have a pair of opposite spin electrons. But in antiferromagnets, it's obviously much easier to make a Cooper pair.
Okay, thank you. Another question by Julian. Actually, two questions. Is the collinear spin texture protected by symmetry, and will it survive in the relativistic case?
Yes, thank you. Very nice question. Yes, so what I try to show is that you can, for every material in a non-relativistic, every collinear non-relativistic magnet, you can assign it one of these 11 plus 11 plus 10 spin groups. And if the spin group is one of the 10 ultramagnetic, that means that the two opposite sublattices are connected by a rotation symmetry, not by inversion. In this case, for each of these 10 groups, you can tell what is going to be the topology of this spin texture, if you want, or the spin momentum interaction. It's defined by the symmetry. And it's not that every group has a different topology. You have less topologies than groups. So several groups have the same topology of the spin momentum interaction. But it's very important, again, to emphasize that this is not like the texture you know from relativity, because it's really collinear systems. So you have a spin up, spin up, spin up, and suddenly it switches and it spin down in the next part of the Brillouin zone, and again it switches. Now your question is whether this is going to survive relativity. It's a very good question. It certainly will, because and it's also been confirmed by density functional or first principles calculations. And the reason for this is that this effect, this non-relativistic altermagnetism, is a much stronger phenomenon than relativity. Relativity is typically a correction, while this still originates from a strong non-relativistic physics, which is as strong as, let's say, the non-relativistic ferromagnetism. So yes, ultimately all the systems are relativistic, but in most of these altermagnets, if you turn on the relativity, it will just be a small correction. So for example, if you have band crossings somewhere, they will open a small gap. And around this small gap, you will have rotated spins, non-collinear spins. But once you go away from this anti-crossing, you will have a very perfectly collinear still spins where the relativity will play only a minor.
Okay, thank you. Jorge Lobocheca wants to know if, can you translate these antiferromagnetism results to ferrimagnets?
Yes, again, thank you. It's a very good question. So in our terminology, ferrimagnets would be actually identical to ferromagnets, meaning that already on the level of non-relativistic exchange physics, ferrimagnet has a net moment, which is given by the exchange. And the reason is that, yes, you may have two sublattices, but there is no symmetry operation by which you can map one sublattice on the opposite one. They are simply different type of sublattices. They have different symmetries, and you cannot map one onto the other. So there is no physics, there is no symmetry that imposes that the two sublattices have the same moment. And then whether they are coupled parallel or anti-parallel, it still doesn't matter. There will be a net magnetic moment because of the exchange interaction, and because symmetry does not impose the two moments to have the equal magnitude. So from this perspective, they would fall into our terminology, they will fall in the category of ferromagnets. And indeed, they have many properties which are similar to ferromagnets. And to get, for example, in ferrimagnets, zero net moment, typically it's only accidental. For example, at some temperatures, you have accidental compensation of the moments, etc. So I hope that answered the question.
Good. Next question, Marina Ferreira. Thank you for the very interesting and didactic talk. I was curious on whether there is any material that displays a transition, for example, with pressure or temperature, between the altermagnet state to a D-wave superconducting state.
So thank you very much for the question. So this is a question for future research. So I encourage you to get involved in this research, which I think it could be potentially very interesting. So it has not been done. In fact, this altermagnetism has been identified only very recently. But remarkably, the parent cuprate happens to be altermagnet, even though if you would search the literature, people would ignore this spin splitting. They would think that it's antiferromagnet. It's been known that it has a compensated state. And to get a transition from an antiferromagnet to an altermagnet, what you need to have is actually to somehow lower the symmetries. You have to break the inversion connection between the two sublattices into something which is a lower symmetry and is just a rotation. And the rotation is such that you have the two sublattices whose anisotropy axes are tilted. And this is what indeed happens in these cuprates. They don't have a perfectly aligned symmetries of the two sublattices, but they are mutually tilted, but you can still connect them with rotation. And that imposes the same magnitude of moments, opposite orientation, but simultaneously opens the spin polarization in their electronic structure. And remarkably, the symmetry or the topology is of a D-wave character. So nobody yet explored whether this has anything to do with the D-wave character of the superconducting gap, but it is suspicious. So it might be worth certainly exploring.
Okay. Next question, Jose Solano, if in ferromagnets exchange interaction causes the splitting of bands, and in altermagnets, what energy causes the splitting? Why is it more energetically favorable than no polarized bands?
So thank you very much for the question. Can I still share the screen? Is it possible? Because it would help me a lot if I can open a slide.
Yeah, I think you should be able.
Okay, so let me just again share the screen. Thank you for this question, because I was running out of time and I didn't have time to properly explain what is actually determining the size of the splitting in these altermagnets. And it is seen on this view graph here. So in a ferromagnets, what splits the bands is the exchange field. In an antiferromagnet, you of course also have an exchange field because you have these strong moments on the sublattices. But what happens, and you do have the band splitting by the exchange field. But what happens is that because of the symmetry of the antiferromagnet, you have a spin up and spin down state mixed at a K vector, and the opposite spin mixture you have at this higher energy. So the states are spin unpolarized, but the two bands are split by exchange interaction. And in altermagnets, you have also this exchange splitting of the bands, as you see here. But what determines the separation of the spin here is not the exchange field, but it's actually crystal field splitting. What happens is that now in this altermagnet, it's not the same, it's not that you have at the same K vector a mixture from both sublattices. This rotation symmetry moves the opposite sublattice to another K vector. So now you have to actually go with the sublattice and see what happens for the purple sublattice when you go back to the original K vector. And you see that it has a higher energy. And why it has a higher energy, this sublattice at this momentum K, is because there is an anisotropy. So there's a local anisotropy of the purple sublattices, which makes the energy at K prime vector different than when you rotate the K vector by 90 degrees. So the local anisotropy, which causes a crystal field splitting, electrostatic, not magnetic, electrostatic crystal field splitting, is what generates the splitting, the spin splitting at a given K vector. So you have a combination of exchange, which actually does split the structure in these two pairs, but the separation at a given momentum of the two nearby bands is determined by electrostatic crystal field splitting. So to maximize this, you need to have a nice anisotropy, local anisotropy of these bands. And then as an example of such an anisotropic crystal, I can show you here, for example, this potassium ruthenium oxide, where you see that the octahedra around each sublattice are strongly anisotropic, and they are rotated between the two sublattices by 90 degrees with respect to each other. So there's a rotation symmetry that connects them, and there is a strong local anisotropy which causes a very large crystal field splitting, which is equivalent then to the spin splitting. Okay, thank you.
So thank you. Question by Pradi. Thanks for the very nice talk. Can I understand this way that altermagnets are also another class of antiferromagnets? If not, then what would it be? Their temperature-dependent behavior will be compared to ferromagnets or antiferromagnets? How will be also the magnetic hysteresis in altermagnets?
So thank you very much for the question. So it's a matter of taste. How do you consider the delimitation? It's similar to if you think of nail. At the time of nail in 1930s, there was only one big class of magnetic materials, and then there were some anomalies. And then Nail decided to delimit a separate class of antiferromagnets, and then it stopped being an anomaly the phenomena, but they actually became a regular phenomenology of a different class. So there's been several reports in recent years of anomalies in antiferromagnets. Like, for example, people noticed that there can be spin polarization in bands, in non-relativistic bands. And so there were reports of several materials with these anomalies. So what we did, instead of calling these anomalies of an antiferromagnet, we went back to the basic symmetry theory and delimited altermagnets as a separate class. So now, if you see a spin splitting in a non-relativistic band structure, it's not in our picture an anomaly of an antiferromagnet, but it's actually a regular feature of a symmetry-defined class, which is nearly as abundant as spin unpolarized antiferromagnets or spin polarized ferromagnets. So this is the first part of the question. It's a matter of taste. If you want to say that altermagnets are delimited or part of antiferromagnets, certainly from the symmetry perspective, you can see that the algebra of the symmetry groups which describe altermagnets is completely distinct from the algebra describing unpolarized antiferromagnets, and again, completely different from ferromagnets. Now, in terms of hysteresis, many of the thermodynamic properties, this is again something which is virtually unexplored. People have not discussed for many years the spin polarization physics because it was not known. The first reports are only a couple of years ago that antiferromagnets can have the spin polarized bands. So I think that now there is time to come back to the very fundamentals and start to see if we fully understand thermodynamics, hysteresis, and all that. Now understanding that the physics of compensated systems is much richer than what we thought originally. We think that, for example, switching in magnetic fields would be very different in altermagnets than the simple spin flop switching that is understood in antiferromagnets, etc. But again, this is an area which is completely unexplored, and we're more than inviting everybody to take a look at this.
Okay, so thank you very much, Professor Jungwirth.